Hello everybody, this is a quick video on this worksheet for polynomial graphs and zeros. It goes with the day one notes that we were working on in class. And we're going to jump right into number one. Number one says, sketch the graph of a quadratic function with the given number of zeros. So I'm actually going to give you how many zeros each graph will have. But before I do that, I want to note that we are specifically talking about, let me get my highlighter here, quadratic functions, which means I know right away the two options for this graph are that it has a single turn. Those are the two possibilities. So the first one I'm going to ask you for is two real zeros, which means that there will be two x-intercepts and no imaginary. That's how I'm going to write my zero. No imaginaries. Well, for there to be two real x-intercepts, my graph would have to look something like this, or it could be the same, but opening down. Here's one. Here's two. Next, two, again, two real zeros, but only one x-intercept. And you may be saying, well, wait, if there's two real zeros, shouldn't there be two x-intercepts? The answer is no. Think back, oh, and this will be no imaginary. Think back to our repeated zeros, where when you solved something, you don't have to write this down, but it was something like this. That would mean x minus 5 times x minus 5, it's repeated. Even though you have two binomials here, they both get you the same answer of x equals 5. So it's repeated, which would look like the graph where the vertex sits right on the x-axis. So we have two real zeros, but only one x-intercept because it repeats itself at the same x value. And lastly, no real zeros, meaning that we have two imaginary. Can you think of what that would look like? Recall from our previous work on transformations, that would be a graph that it has been a quadratic that has been shifted down and opens down. That will have two imaginaries, or it could be shifted up, opens up. If you wanted to add a second example for this one without interfering with that graph, it could open down and sit right on the x-axis. The vertex is right on the x-axis. I'm not going to draw a second example for this one because I don't want it to conflict with what I drew right here. So quadratics we're familiar with. I'm hoping that as I talked about this, our prior work with transformations and shifts came back to you. The new part is really specifying how many real zeros versus intercepts and how many imaginary. So pay attention to these two cases where in both A and B you had two real zeros, but in this instance we have two x-intercepts, and in this one we only had one because of that repeated value. Number two says, sketch the graph of a cubic function. Let's highlight cubic. Because it's cubic, cubic means degree 3. If I asked you how many turns, you would think, well, degree 3, 3 minus 1 is 2. So 2 turns. the possible cases are 3 real zeros with 3 x-intercepts, 3 real zeros with 2 x-intercepts, 1 real zero, 1 x-intercept. This would have no imaginary, and this would have 2. So let's start with case A, where we have 3 real zeros and 3 x-intercepts. Could be increasing or decreasing. We're just going to draw all these increasing. So 1, 2, 3. When I was doing my count of 1, 2, 3, I was saying crossed once, twice, 3 times. And if I check, I'm supposed to have 2 turns. I have a turn right there and a turn right there. I'm in good shape. Now for example B here, we're going to have a situation where there's 3 real zeros, but only 2 x-intercepts, which means one of them repeats. So let's see what that will look like. 1, it touches, it does not cross. 2. Here's 1, 2. And I still have 2 turns. 1 turn, second turn. Last but not least, only 1 real zero where I have 1 x-intercept, 2 imaginary. So think of how you can draw this, that it crosses once, turns, but that's the only x-intercept I've got. So it's going to turn and not cross again. There's my 1, 0, my 1 real x-intercept. So for cubics, these are the only 3 possibilities. Let's move on talking about quartics. Oops. I think my pages got a little out of order. All right. Quartics. I know it's a 4th degree. So I have 3 turns. Moving up. Quadratics had 1, cubics had 2. Now we're at quartics, which will have 3 turns. Let me set up what we'll be working with. A will be 2 real zeros, 2 x-intercepts with 2 imaginary. Example B will be, or case B will be 4 real zeros, 2 x-intercepts, no imaginary. And then here we're going to have no real zeros, 4 imaginary. So before you even try to graph this, if it helps, think of what quartics look like in general. It's an even degree, so they could open up or down. For the sake of the notes, I'm going to go, maybe some will have open up, some will have open down. That's not the point of the sketch. But think about what it means, 3 turns. So 1, 2, 3. 1, 2, 3. Or if I had sketched it with opening down, both ends, the end behavior is down. 1, 2, 3. When I'm making that count, I'm tracking my changes in direction. 1, 2, 3. So all 3 of these graphs will look something like this. The difference is how many times we will cross the x-axis to have these x-intercepts. So our case A, I'm going to have 2 x-intercepts. Cross once. There's a 1 turn, 2, 3 turns, and then I get my second x-intercept. So half of this is knowing what the graph should actually look like, and the other half is how do I manipulate the graph to sketch the given number of x-intercepts. So here I knew that this was going to look like a W, and it's going to cross twice. Next, case B, we have 4 real zeros, but only 2 x-intercepts. So here, like, these match exactly. 2 reals, 2 x-intercepts. But notice, now I've got 4 real answers, but only 2 x-intercepts. So this is an example where we're going to have repeated zeros, meaning it's only going to touch twice. 1, 2. So these are both repeated zeros. Last but not least, no real zeros, so I have no x-intercepts of any kind. They're all imaginary. How would you sketch this so that you never cross the x-axis? Well, just like before, the whole graph is shifted up and opens up, or the whole graph is shifted down and opens down. But notice there is no contact whatsoever with the x-axis. Last but not least, we have these 3. So let's say I have 4 real zeros and 3 x-intercepts. No imaginary, I think. I might fill that in a second. Let's graph 3 x-intercepts, and then we'll come back to the imaginary. So remember, off to the side or in your brain, you're thinking it's going to look something like that or something like this. So I've got 1, 2, 3. Oops, that doesn't work. 1, 2, 3, and I'm done. 1, 2, 3. So no imaginaries here. We could have 4 real zeros and 4 x-intercepts. No imaginaries. That would look like what I was about to do, which is I go 1, 2, 3, 4. We cross 4 times. 1, 2, 3, 4. And last but not least, 2 real zeros with only 1 x-intercept, which means I have 2 imaginaries. So this entire time, I am mentally saying, well, the number of reals and the number of imaginaries has to add to 4. So if there's only 2 real, there has to be 2 imaginary. Here, if I have 4 real, there's no imaginary. 4 real, no imaginary. 2 reals, 2 imaginaries, that equals 4. I had 4, none, none, 4. And then up here, before. Here we had a max of 3. If there was 3 real, none. 3 real, none. If there's only 1 real, automatically 2 imaginary. So it adds to the number of, it adds to the degree. So coming back to our last example, this is a degree 4 polynomial, so I should have 4 zeros. This is an example where 2 of them are real, 2 are imaginary. So how do I graph this where of my real zeros, there's only 1 x-intercept? Well, it's going to touch once and never touch that x-axis or cross it ever again. I have 1 x-intercept. This comes with practice, so if we're sketching with a pencil and something doesn't come out right, it's not too bad to go back and adjust our picture. So use this as a guide to help with the homework worksheet, and any and all questions, shoot me a remind, and we will pick up this conversation tomorrow in class. Have a good day.